Well, for the next couple minutes, guys, what I want to have you guys learn about is this idea of linear programming. And the big idea of linear programming is this idea of optimization. So when I look at the idea of optimization, what I'm trying to do is I'm trying to find maximums and minimum value of each quantity. And linear programming is the process of optimizing a linear objective function subject to a system of linear inequalities called constraints. So what we're going to do is we're going to graph a system of linear inequalities, which we talked about today, and we want to try to find some minimum and maximum values of this thing called a linear objective function. Okay? And when I look at the graph of these system of linear inequalities, I get something called a feasible region, which is the graph. It's the graph of the constraints, the graph of the system of constraints. Now, when I look at my feasible region, I have two possible solutions or two optimal regions that I get. One is bounded, which means that it's just enclosed all the way. So in this case, this is an example of a bounded region right here. That there's like four sides to it, and all the shaded region is inside. Another example of something is called an unbounded region, which what happens is there's like an infinite amount of solutions like in this area right here. Okay? So what I want to do is I want to graph. I want to solve this linear programming question. So right here, this is my objective function. Okay, and these are my constraints. So when I do these problems, what I want to do is I want to graph my constraints first. So the first thing we want to do is graph constraints. Okay? So the first one is x is greater than or equal to 0. So when I look at this, this is where x equals 0. And what I know is I want to graph all the solutions in which x is greater than or equal to 0. So what I know right now is that on this side of this line, those are my solutions. Okay? Now I want to graph my second line, which is y is greater than or equal to 0. And my solutions are going to be up here, but the intersection's right here. So right now, I know this is my possible solution area. So I don't even have to worry about down here at all. So in theory, I could just kind of get rid of this because I know that my solutions are going to be in quadrant 1. So the next one I want to graph is x plus y is less than or equal to 8. So I know that my x-intercept is 8, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And my y-intercept is 8, so 2, 3, 4, 5, 6, 7, 8. So this is what your line's going to look like. So if I plug the point 0, 0 into this system, is 0 smaller than 8? Yes. So what happens is my solution area is actually this triangle right here. This big this triangle right here. And when I look at my solutions, I have 1, 2, 3. Now, how do I know that? This is where my lines intersect the other lines that I drew. Okay? And this is my set. So I have a triangle. What are my vertices of my triangle? It's where the lines intersect each other. So I have 3 solution points. I have the point 0, 0. I have the point 8, 0. And I have the other point 0, 8. Now what I want to do is I want to find out which one of these are my minimum or maximum value of my objective function right here. So all I have to do is plug each of these points into this equation to get a specific value. So I do c equals 3 times 0 plus 4 times 0, and I get c to be 0. Okay? Then I do the same thing with 8, 0. So I got 3 times 8 plus 4 times 0. Well, I get 24. And then I do 0, 8, and I got C equals 3 times 0 plus 4 times 8, and I got 32. Okay. Now, when I have a bounded region, I will always have a minimum and a maximum. All right. Well, what's my smallest value? 0. When I plugged up 0, 0 into my objective function, I got 0. So therefore, 0, 0 is my minimum value. Okay. And then I got 24 and 32. Well, 32 is larger than 24. That means that 0, 8 is my max. Okay. So what I have is I have my max be 32 at 0, 8. And then my min of 0 at 0, 0. What I encourage you guys to do is try one. I would stop it right now. Try it, and then the next page has the solution. Well, hopefully you guys had a chance to stop it. This is what your region should look like. And what I got my minimum to be was at -5 at the point 50. And then my max was at 2, 8. Well, these are examples of bounded regions. Well, now we want to look at something in which it's an unbounded region. Okay? So, I want to graph both of these inequalities. So, x is greater than or equal to 0. I know that it's going to be shaded this way. Then I want to do y is greater than or equal to 0. Sorry about my lines, guys. So right now, I know my solution is going to be in this region right here, that quadrant 1. I want to graph that second line. So that's x plus y. So my x-intercept is at 5. And my y-intercept is at 5. So 1, 2, 3, 4, 5. All right. So right now, x plus y is greater than or equal to 5. I know 0, 0 does not make that true, so I know my solution area is up here so far. Okay, so I want to graph one more line. I want to graph this line right here. My x-intercept is at 6. And my y-intercept is at 4.5. 2, 3, 4 and a half. So I'm just going to draw a line connecting the two dots together. So there's my line. Okay? So 0, 0 does not make it true. So what happens is I know that my solutions are around here. So I have an unbounded region. Now, how many solution points do I have that creates this region? I have, it looks like I have one right here. I have another right here. This is where 3x plus 4y equals 18 intersects x plus y equals 5. And this is where, this point was where x plus y equals 5 intersects x equals 0. And I'm looking at 3x plus 4y equals 18 intersects right here. So I have 3 solution points. My 3 solution points are 6, 0. And I also have a point at 0, 5. 0, 5. And my other one looks like it's at 2, 3. Okay? 2, 3. 2 plus 3 equals 5. That works. 3 times 2 is 6 plus 12 equals 18. So that's why those are my solution points. I'm going to plug each of these in to my objective function. which is 5x plus 6y. All right. Well, if I do that, I get 30. I get 30. And then I have 10 plus 18 is 28. Now, when I have unbounded regions, I will either have a minimum or a maximum value. How do I figure out if it's going to be a minimum or maximum? What I do is I just choose a point. I'm going to just choose like the point 10, 10. 10, 10 is in my solution area. Okay? And I want to see, are these values smaller than that value in my feasible region, or is it bigger than it? So if I plug 10, 10 into this, if I plug the point 10, 10, which is like right here, if I do 5 times 10 plus 6 times 10, looks like I get 110. So all these values are smaller than 110, and that's in my feasible region. Therefore, I'm just looking for a minimum value. And in this case, my minimum would just be this point right here, because 28 is smaller than all the other ones. Okay? So I want you guys to try to graph the next one, and then look at the slide after this. So this is what your final solution should look like. There would only be 2 points of importance, of 2 points of intersection. That creates my feasible region. They would be at 0, 2, and at 1, 4. And 1, 4 would turn out to be a max, because if I plug a point that's in my feasible region, like 2, 0, it is smaller than both of these values. Therefore, I'm just looking for a max value. Thanks for listening. We'll talk about it more tomorrow.